Hello, this is our final project for the Analytics Edge class. We present beer reviews from beer advocates. This work is presented by Edgar, John, and Tanner. Business is booming. That is a fact. US beer market is estimated at $100 billion. Craft beer sales make up 25% of the overall market, while only 13% of the volume. The table below shows the evolution of the beer market over the last 6 years. This is a snapshot of the Beer Advocate website. Beer Advocate and Untappd are popular online communities for beer reviews. They have a top list of beers and recommendations. Our dataset contains over 1.5 million observations and 13 variables. The head shows the top first rows of the dataset. We experienced issues with factors. The dataset contained approximately 57,000 different beers from 5,700 breweries. Multiple predictors were treated as factors with several levels. This led to extremely long processing times for the models to run, specifically CART and Random Forest.
As Edgar alluded to in the last couple of slides, we had quite a few beer reviews, 1.5 million to be exact. So we had to reduce our data sets for our training pipelines. This would allow us to run our reviews with fewer training samples. And then on the full data set, we used an AWS instance to run our regressors. These regressors would take anywhere from 30 minutes to a couple of hours. We also had to do a lot of data cleaning. We had to reduce our breweries, reduce our beer reviews, reviewers, and so on and so forth. And we'll talk more about that as we go through each of our regressors. All right, let's talk about cleaning the data set for the recommender algorithm. So we started out with just under 1.6 million reviews. We had to remove around 100,000 of those reviews because of incomplete data. So we were left with around 1.5 million reviews. From there, we generated a unique ID for each beer reviewer, review ID. You can see that on the right here. The review ID was then set to a factor. We then removed all beers and reviews with less than 50 reviews. We found it was quite difficult to recommend a beer to a reviewer, a specific person, if they'd only reviewed 1 or 2 beers. Finally, we set the ratings from 1 to 5. So any rating that was above a 5 or less than a 1, that review, that specific row was dropped from the dataset. Then we removed the extra columns and split into the test and training data sets. You can see the sample over here on the right. The training set had around 1 million reviews, and we did a 99% split as you saw in class. Once we had that data cleaned, we used the cv.recommender function that was provided in class. We ran the clean data through the recommender on our AWS server after we had ran a couple iterations of testing. The reviews were highly clustered around 4, which made for a lot of issues, and it caused our initial R-squared to be around -50. Essentially, this means that we were better off just picking the average by like 50 times than actually using our algorithm. But finally, we were able to get it kind of sorted out and worked out, so we got our R-squared around 0.15. Next, we'll move on to the logistic regression and the cleaning that we had to do for that data set. So we started off similar to the last one, the recommender. We removed all rows in which columns were not properly filled out, which left us with about 1.5 million reviews. Then we removed all beers and reviewers with less than 50 reviews, similar to last time. But for this one, we kept in breweries and beer styles, but removed any breweries or beer styles that had less than 1,000 reviews. This allowed us to really kind of hone in our data set and get specifically what we were looking for, it helped us with our R squared kind of at the end as well. We were able to get our training set rows around 673,000. In running the logistic regression, we tried to see if a user would rate a beer 4 stars or higher. We used the clean data set that I mentioned on the last slide with 673,000 reviews. Initially, we just tried our prediction at 0.5 with fairly good results. We got an accuracy of about 0.71 with a true positive rate of 0.93 and a false positive rate of 0.73. However, when you go to a brewery, you have 5 to 10 beers to choose from. You probably don't care about the true positive or the accuracy. You care about whether or not you're predicting a bad beer, right? You want to only predict good beers. So we set the prediction rate to a higher 0.8, and we were able to get the false positive rate down to 0.078, which we thought was probably a better algorithm for the users.
Hello, my name is John, and I am going to be presenting our cart and random force models and then doing a final summary and a little cross comparison of all of the models that we presented. As that was mentioned earlier, there was some issues with these two models and the excessive levels of factors that was presented by Edgar earlier. Specifically, we had issues with the beer style and the brewery name column. There were just too many levels, and so it was taking an extremely long time to process all of those in the models. So we had to do two things. The first thing was to filter all of the beer types to only include beer styles that included the word American in them. So pretty much all of the American style L's were left. And then also we had to limit the number of breweries to the top 75 breweries. And this really didn't change the overall size of the data set too much. We still had about 390,000 reviews to work with to train the model and whatnot. So we kept the same strategy for the split that we used in the model earlier. Next, I will quickly run over the results of our initial cart classification model. So we just did the regular cart here, and I also need to introduce our baseline because we'll compare some of our models back to that throughout the remainder of the presentation. So Tanner presented the distribution of the data earlier, and we saw that there was a lot of the 4 rankings. So we're going to go ahead and assume our baseline as if we have predicted 4 every time, and you can see that is about 70% accurate. We got really the similar results as the logistic regression, just maybe a little better if you compare against AUC, but really same story here is that there's high TPRs, high FPRs, and high accuracies. The min bucket perimeter really had no effect on the model results. And as we lowered the CP parameter, it quickly started overfitting the model. However, we did manage to get some pretty good visual cart classification trees out of our data set. Here you can see 2 trees that represent the data that was presented on the previous slide. On the left, the tree has a higher value of CP, so you can see it doesn't have as many leaves or nodes as the one on the right, which has a much lower CP value. You can definitely see the one on the right has a lot more overfitting than the one on the left. And throughout all of these classification trees, it's going to be really hard for you to see what is within some of the splits, but essentially the brewery name is the most important predictor. Beer style comes out second, and the ABV is third. The next step we did was do a cart model with cross-validation. As our mission is to reduce the number of false positives that our model predicts, we ran a sensitivity and tuned the model by applying a loss matrix. we did 3 cross-validation models with 10 folds each, and through each of those we applied the LFP term of 1, 2, and 5. Here you can see the results from those models. We just plotted number 1 and 5. You can see that they have just slightly better performance than the regular CART model, and the downside to applying the loss matrix is that it immediately and severely overplots your data, or overfits your data, and you get some pretty crazy plots. Here we actually had to raise the min bucket up to 200 just to tame it back a little bit more and fit on the slide here. Before I get too far into the final results, we did also run a random force model. We did have a lot of issues with the random force, especially when trying to run it with cross-validation. It was taking all night to run, and we were getting a lot of errors, and so we really didn't have the time to fully troubleshoot it and figure out what was going on. So we just did a regular random force model to compare against the other CART classification models. And for a random force model, we really struggled to penalize the false positive rate. I think that we penalized it as much as we could. We used the cutoff function within the random force function in R to raise the cutoff before it classifies it as a 1 or 0, and that really seemed to drop the FPR from about 0.7 to 0.73 to 0.58. So when looking at all of our models in comparison, really the CART, where we applied the cross-validation and the LFP term of 5, gave us our best results. It had a 42% accuracy, fault positive rate, which what we were going for is a 0.06, while still maintaining a 0.21 true positive rate. If we take a look at all of our models in comparison that we have walked through in terms of classification, we can see there are C curves presented in this plot here, and we can see that the cross-validation CART model with the LFP 5 does the best performance. The baseline is in red, and really all of the cross-validations were the best performing compared to the other models that we ran. So if there's any questions regarding any of the information we presented, you can feel free to email us at the emails